So conditional probability makes the whole probability system so much more useful. Conditional probabilities lets us ask questions like, if I observe one thing, what can I learn about another from it? We're almost always doing that in research. If I observe this data, how does that change my beliefs about other things that I'm interested in here? Okay, so the way we write conditional probability is like this. The probability of E conditional on F is the probability of this definition, E intersect F divided by the probability of F. Okay, so this is our definition. And let's annotate this maybe a little bit further. This bar here, that's the thing we read given or conditional on. And what it is doing is it's separating the things we're still uncertain about on the left side from the things that are now known. Okay, so we might contrast this with probability of E. Here we're assuming F is not known. F is still random. But once we add the conditional on F, it's like, okay, now we've learned something new. Do we want to adjust our beliefs about E here? So everything that occurs or that is written on the right-hand side of the bar are things that are no longer uncertain. They're the world we're living in. They are now to be given here. Okay, so with that in mind, let's think about the logic of the definition here. So in saying I want the probability of E conditional on F, it's like F is reality. F is true. F has happened. So the only way that E is going to happen is E intersect F. The only part of E that can occur is the part of E that overlaps with F, because F has happened. We're not uncertain about it anymore. Okay, so it's really the joint probability has got to be up there in the numerator. And down here in the denominator, we need to have the probability of the conditioning event in order for the probability of E conditional on F and E complement conditional on F to sum to 1. Okay, and they got to do that because they're probability function just like any other one. So maybe even write that second point there. Necessary for the probability of E conditional on F plus complement conditional on F to sum to 1. Okay, that's got to be true. In the world where F has happened, in the world where we're conditioning on F, probability's got to obey the Kolmogorov axioms no matter what F is. Okay, there's no rules about what happens in the world of F versus the world of not F. Those are separate worlds. No requirements between them. Okay. So let's get going on an example here. And for our example, we'll have coin flips. 2 of them, HH, HT, TH, and TT. And let's have some events here. So let event E be, what do I want E to be? HH, HT, that would be, make my bracket curly the way it's supposed to be. So event E is the event that the first flip is heads. So I would say that in English. Okay, first flip, heads. And while we're admiring E, we might know that the probability of E, we're going to assume it's a fair coin throughout this example, is 0.5. And another event here might be F. What is F? F is HT, TH, TT. So saying that event in English, I might say that's at least 1 tails. looks like that's what those outcomes work out to. And so then the probability of F here is 0.75. Okay, so say we don't observe the coin flips, and initially I asked you what's the probability that the first flip is heads, and you know that the probability of each of those things is a quarter, and so probability of that event is 1/2. Fine, that's your probability of E. Now I tell you, well, suppose I'm letting you know that there is at least one tails. Does that change your beliefs about E? It should change your beliefs about E if the conditional probability is different than the what we call the prior probability or the unconditional probability. So let's check. Let's look. Is the probability of E conditional on F equal to the probability of E? If it is equal, we didn't learn anything from F. If they're not equal, it means, yeah, F taught us something. So using the formula here, probability of E conditional on F is, so let's see, I'll need to calculate the probability of E intersect F here. So let me just write that over there. Maybe I'll change my color here. E intersect F is, let's see, looks like just HT, right? That's the only thing that's both in E and in F here. Okay, and so the probability of conditional on F is 0.25. So I'm going to write that in over here, 0.25. And the probability of F, we already calculated. It's right here. 0.75. So the probability of E conditional on F is a third, 0.33. So yes, it is different. No. Yes, it is different. No, they are not equal. The conditional probability does not equal to the probability of E. It means we learned something. That was valuable information. The fact that there was at least one tails changed our beliefs about the likelihood that the first flip was heads. So that's the kind of learning process the conditional probability helps us think about. Okay. Actually, let me go back to what I just moved here. So in asking this question, though, I'm kind of implying that the answer isn't always yes. Sometimes the conditional probability is different from the prior probability, the probability before we knew whether F was going to happen or not. And sometimes it's the same. When they're the same, we say the events are independent. Okay, so I want to say some things about independence here. And I think I want to first just do another example here. So let's keep E just like it was before, HH, HT, just like it was before, the probability of E is 0.5. But now let's think about a different potential conditioning event. Okay, so G, now G is going to be HH, TH. Okay, so G is saying the second flip was heads, and the probability of G is 0.5. Okay, we can ask the same question here. Is the probability of E conditional on G equal to the initial probability of E? Well, let's see. E intersect G is just HH, right? And the joint probability of E and G is 0.25. One of the four possible equally likely outcomes there. So that's enough to use our formula. Conditional probability is the probability of E and G divided by the probability of G. And again, it's if we're conditioning on G, we know G has occurred, so the only way E could happen is to be is the part of E that overlaps with G. That's the only part of E that can happen. It's the way I want to say that colloquially. And I've got my probability of G there to make the probabilities sum to 1. And then plugging in my numbers here, I've got 0.025 divided by 0.5. Probability of the intersection divided by the probability of the conditioning event. Oh, look. In this case, yes, I don't learn anything from G. It doesn't change my beliefs about E at all. And that is because E and G are independent. Okay. Knowing how the second coin flip came out doesn't tell you anything about how the first coin flip came out. Okay, no gambler's fallacy here. They really are independent. Okay. So the definition of independence, E and F are independent if the probability of E conditional on F equals the probability. Okay, it doesn't change your beliefs. Okay, so what do I want to say about independence here? As researchers, we're often kind of like pulled in two directions about independence. And really the question whether we assume independence in our probability models or not. On the one hand, as theorists, we tend to be skeptical about just saying, oh yeah, that one thing never affects another. It almost seems like you're closing off possibilities. And if you try and assert something like, the shark attacks on a beach shouldn't affect the whether or not an incumbent is reelected or not, people might say, well, hey, wait a minute, maybe they do, maybe they don't. But you don't want to like close off those options. So as theorists, we tend to like the idea of, well, maybe things affect each other, and we can just sort of think about the special case where they might not. So theorists tend to be skeptical about independence assumptions. Once we start trying to test our theories with data, though, then we have to start appreciating how simpler our lives are if we make those independence assumptions. Okay, so there's always going to be this kind of seesaw here. And I think in your substantive course, there's a lot of the arguments you'll be having in the context of the things that you're reading will be about, well, people assume that this thing doesn't matter, and I'm saying that it might. And then the author, who may or may not be available to defend their paper, will say, well, yeah, your thing might be true, but my model's already really complicated. I can't measure the thing you're thinking about, that kind of thing. So there's a basic trade-off in social science work there. The other thing I want to say about independence, it's got a little more of a concrete punchline to it, is when, but only when, big emphasis here, E and F are independent, then we can calculate the probability of the intersection by multiplying the probabilities. Okay, so when and only when they're independent, the probability of E intersect F equals the probability of E times the probability of F. Okay, and you can see that follows right from the definition. Okay, if the probability, conditional probability is the same as the unconditional probability, that's what it means for them to be independent, then the probability of E has to equal that joint probability divided by F. And so just rearranging this gets you that. Okay, but this step requires independence. Okay. We can calculate the probability of the intersection in any case, whether they're independent or not. Let me write it differently. The probability of E intersect F equals the conditional probability divided by the probability of F. This one is always true, whether or not they're independent. Okay. In terms of figuring out the probabilities, though, this figuring out the conditional probability can get a little bit more complicated. So I'm kind of belaboring this because many of you guys come to grad school and you've had an undergraduate statistics class, and that's probably where you picked up the probability that you know at this point. And in those classes, you probably assumed that your data points were independent of each other. And you made that assumption because you wanted to calculate joint probabilities by multiplying them together. Okay, and that if that's sort of your first experience with calculating joint probabilities, often in those kinds of data-focused basic statistics classes, they don't make a big deal about the independence assumption. It might not have hit you that that's a pretty restrictive assumption. Okay, so here in this class where we're doing probability theory, we want to be self-conscious about independence assumptions. We don't want to be making them in kind of an unthinking way. And we particularly do not want to be multiplying just the basic probabilities together to get a joint probability in a situation where it's not plausible to for them to be independent. Okay, so we'll be revisiting points about independence at various points throughout the course, but we'll go on to the next lesson and look at some ways of depicting conditional probability.